This is section 5.4, using similar triangles, and I think you can guess what we're going to do in this section. We are going to use similar triangles, but what are we going to use them for? Ultimately, we're going to be trying to find the height of unknown objects, or a distance, like across a lake. So on this one, we're trying to find the height of a flagpole. We could call that x, and we're going to use some similar triangles to help us do that, or the distance across a pond, so we don't have to go swimming across that pond, and we've got some known distances on land here. All right, so before we can get to those examples, what we're going to be looking at is 3 vocab terms. The first one is similar triangles. If we're going to use them, we have to know what they are. So similar triangles are triangles with the same shape, but not necessarily the same size. And I put a note here saying that similar triangles have the same angle measures. That's what I mean by the same shape. They all have the same angle measures. So all of these triangles, I could take any one of them and stretch or shrink it to get to the other triangle. So if I just stretch this one out, right there. Okay, I could stretch them out and make them the exact same. So they are similar because you can stretch them or shrink them and they become the same shape. One that would not be similar to those is if I make a right triangle. A right triangle right here, I've got that 90-degree angle measure. If I try to spin this around and try to match it up, it's never going to be able to match up with that other triangle. So the reason for that is they don't have all the same angle measures. So you can tell that all 3 angles here are acute angles. This one has that right angle right there, so there's no way to match these up without changing the shape. All right, so let's keep moving. So in order to find those heights or distances, we have to do 2 more things, and that is talk about what you see in the directions right here, indirect measurement. Indirect measurement is using similar figures to find a missing measure when it's difficult to find directly, like climbing up a flagpole or swimming across a pond. So we're going to indirectly measure those different distances. And we're going to do that by setting up a proportion, and that is a comparison of fractions using an equal sign. So proportion could be simply something like 1/2 equals 2/4. They are equivalent expressions. But today I'm not going to have numbers in all these spots. I'm not going to know one of those numbers. So it'd be something like x divided by 2 equals 2 divided by 4. And then how would you solve an equation like this? That goes back to chapter 1. You have to undo the division by multiplying both sides by 2. So that would cancel out the dividing by 2. Remember, a whole number is the same thing as that number over 1. And to multiply fractions, you multiply straight across. So all of these questions that we're going to be doing today, you're going to set up a proportion. Well, the last one, you're just finding angle measures, so I shouldn't say all of them. But most of them, you're going to set up a proportion, and then you're going to multiply both sides, turn it into a fraction by putting it over 1, and multiply straight across. So 2 times 2 is 4. The denominator, 4 times 1 is 4, and 4 divided by 4 is 1. So that is how we're going to be solving these proportions today. All right, let's get to some examples. So for the first example, it is some similar rectangles. It says in the directions that the rectangles are similar. And then find x by setting up a proportion. All right, so this triangle is just a shrunken down version of the other one because it says that they are similar. So they have to have all the same angles. It's just shrunken down uniformly. So here's how we're going to set up a proportion. We are going to take any 2 sides and divide them. So I'm going to start with my variable. It's always easiest to put the variable in the numerator. I'm going to start with my variable and say x divided by some other side length. Well, I know this side length, so let's do x divided by 12 equals. I'm only going to have an equivalent expression to this expression if I take the same 2 relative position lengths from the other shape. What I mean by that is I started with this vertical piece, the smaller side length of the 2. So I need to start with the vertical piece here, the smaller side length of the 2. I need to start with the 2 in my numerator. So since I started with this smaller piece of this rectangle, I have to start the smaller piece of this rectangle. And then I divided by the longer side length of this rectangle, so then I have to divide by the longer side length of this rectangle. So I did x divided by 12. It should equal 2 divided by 4. That's how we're going to set up these proportions today. So you take one side and divide by another one, and then you have to look for the same relative positions in the other figure, and again, set up a fraction, 2 divided by 4 in this case. And just like the problem I was doing over here, we're going to solve this in the same way. We multiply both sides by 12 to undo dividing by 12. That cancels out that division. We turn 12 into 12 over 1. And then we can multiply these fractions straight across. So x equals 2 times 12 is 24, divided by 4 times 1 is 4. So x equals 24 divided by 4 is 6. And that is what we're going to be doing today. So let's look at this example, finding the height of a flagpole. All right, so we need to find some similar figures in here. So right here, I've got one large triangle. And then do you see another triangle hiding somewhere in this diagram? Hopefully you see this right here. His height, he forms another triangle right there. So you could do this in real life. You could have someone sitting over here looking up at the top of that flagpole, so you're just looking towards the top of the head, and then it goes all the way up to the top of the flagpole, and then you can measure these different distances, and you can actually find the height of the flagpole. So let's set this up. So again, we're looking for that variable right here. X is the vertical piece of this triangle, so I have x divided by, I only know one other measure, the base of the large triangle. It says is 85 feet, so x divided by 85 equals, again, I started with the vertical piece of this one, so I've got to start with the vertical piece of my small triangle, and it's 6 feet. So equals 6 divided by, I use the base of the large triangle in my denominator here, so I need the base of the small triangle in my denominator here, and that is given as 10 feet. And now I've got that proportion again. Solve it in the same way. Multiply by 85 to undo the dividing by 85. That cancels out. Turn it into a fraction by putting it over 1. And multiply straight across. So x equals 6 times 85 divided by 10. 6 times 85, I believe, is 510. Let me double check that. 85 times 6, yep, 510. And divide by 10. So x equals 0 trick, that's just going to cancel out that 0, and I get 51. And it gives us units on this one, so 51 feet. So that flagpole is 51 feet tall. That's like 5 stories tall. You don't want to climb up a flagpole that's 5 stories tall to try to find its height. So this would be a great use of indirect measurement. All right, the next one, we don't want to go swimming across this pond, so let's see how we can use indirect measurement to find the distance x across this pond. So we are given 2 triangles here. I put a note down here. It says, remember, vertical angles are congruent. So vertical angles are congruent. What that means in this one, we've got an angle here and an angle there that are vertical angles. They're formed by the intersection of 2 lines, and they're directly across from each other. Congruent means they have the same measure. So these have the same measure. We have 2 right angles, 2 90-degree angles. And then we'd have to have the same angle measures for this one and this one, because there's only so many more degrees to go until they add up to 180. So if you have 2 of the same angle measures, you automatically have 3 of the same angle measures. So let's redraw this one so it's a little bit easier to see which side lengths match up with which side lengths. So I'm going to redraw the larger triangle here. There's my right angle. X is this vertical piece, so this is x. The horizontal piece is 30, so this is 30. And it's in feet. And then I'm going to redraw this smaller triangle, but I'm going to spin it around so it looks similar to this one. So I've got the vertical piece there, horizontal piece there. I should draw that a little better. There we go. So I just took this triangle and spun it around. So I can show you on here. You can just do this in your head, but let me show you what this would look like. Let me take a triangle here. All right, so I've got this triangle right here, and I'm just taking it and spinning it around to match up with this one. So right here, that long side is 20 feet. So when I spin this around, that 20 feet is going to get moved over to this side. So when I match it up there, that 20 feet is this vertical piece. So that is 20 feet right here. 20 feet. And then that horizontal piece is 8 feet, the other side length of that triangle that makes up the right angle right here. So that should be 8 feet down on the bottom here as the base. Well, now we can see that we can match these up. This x, I'm going to do x divided by 30. So I have x divided by 30 equals, I started with this vertical piece, so I need to start with this vertical piece, 20 divided by 8. And solve just like the other 2 examples. Multiply by 30 to undo the dividing. That cancels this out. And you have x by itself equals, turn this into a fraction, and multiply straight across. So I have 600 divided by 20 times 30, 600, divided by 8 times 1 is 8. And that is 75. Again, the units are feet, so I need to put 75 feet. And it's the same process as the other examples, but then I know that the distance across this pond is 75 feet. So again, you could do this in real life. You could map out these distances and then just find some object over here like a rock or a tree that you could look at. So you're starting here, going straight across to that rock. You're walking over, measuring the distance on land, which is much easier to do. Walking down, and then once you get to that 20-foot mark, you're looking and seeing where's that rock at, and then you put a little marker there, so you know that that's 8 feet and that's 30 feet. So you could actually do this. All right, the last example. There's a new symbol in this example here. This symbol right here is a math symbol that implies that these triangles are similar. So you'd read this: triangle ABC is similar to triangle CDE. And I've got that note right here. It says find the missing angles. So we've got 4 missing angles. Well, remember from my note, vertical angles are congruent. So right here, this is 50 degrees. This angle right across from the 50 degrees is a vertical angle. So this is congruent. So y must be 50. So this angle measure is 50 degrees. Remember from the last lesson that the interior angle sum of a triangle is 180 degrees. So here I've got 50, another 40. If I add those, I get 90. So x has to be 90 degrees because they'd have to add up to 180. And 90 plus 90 is 180. Well, here it says that the triangles are similar, so I don't have to do any more work. The triangles are similar, so if I were to match these triangles up, the angles have to be the same. So z degrees would match up with x if I spun this triangle around. So z must be 90 as well. And then 40 would match up with w, so w has to be 40 degrees. So that example, not too bad. And that's it. So here's your assignment for this section, pages 210 to 211, numbers 2, 5 through 12, and 15 through 20. Please turn that in on Google Classroom, and if you have any questions, you know what to do. Thank you.